Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and this is part 8 of a little mini-series within that larger playlist. We're looking at two-sided, uniformly most powerful tests in the one-parameter exponential family. In this video, it's an R illustration of the Poisson distribution, which we did in part 7. In part 1, we looked at the theorem that we use to prove that this is a uniformly most powerful two-sided test. And so the null hypothesis is the true lambda parameter less than or equal to 10 or greater than or equal to 12, and the alternative hypothesis is the true lambda parameter between 10 and 12. And that's what this null hypothesis says right here. And I just randomly picked 10 and 12. We're going to let alpha be 0.05, sample size of 25, and we're going to create a matrix of possible C1 and C2 values. We can't do all like we did in the binomial setting because here the support is from 0 to infinity. So we have to pick C1 and 2 values in a smart fashion. And we base it upon the mean observed. And so here the largest possible C2 value would be twice the mean of the larger, the lambda 2. And we just use that for both C1 and C2, and that creates a, possible C1 and C2 values that would be sufficient. And so that's what we just created there. Now, in part 7, we derive what these P1 and P2 P3, P4, and P5 are. They're constant values for a given C1 and C2. Then we derive what the gamma 1 and gamma 2 values must be. We do not want them to be missing. I actually don't remember why I put that in the program. And then we remove those. And then we noted that the gamma 1 and gamma 2 values must be between 0 and 1. That's because they're part of the test function and the values are between 0 and 1. So we only keep those. Now let's check to see if the C1 and C2 values that we kept actually make the side conditions or equations equal alpha. And we print it out and look and notice there's only one that meets all these conditions. And it should, because that theorem says it's a unique value. Both side conditions equal 0.05. Our rejection region is 271 to 277. Gamma is 0.446. Gamma 2 is 986. And that's it. So let's look at the power curve for this setting. So we pick, do we use the C1 and C2 values that we just derived, and then we go through all possible lambda values. And this is it. Notice the null hypothesis was less than or equal to 10 or greater than or equal to 12. And the power curve is less than 0.05 in there. So the size of the test, meaning the maximum probability of rejecting, is 0.05. And it's at these boundary points. And we forced the 10 and 12 to be exactly 0.05. And then the power of the, when the true lambda parameter is between there. Now it's 15% roughly in the middle, 0.05 on the edges, and we'll change this up in a second, but go through this. Now let's do a little computer simulation of, let's say, 500,000 replications. So we're going to create a matrix with 500,000 rows and n, which is 25 columns. And each row will represent a sample of size 25. Then we take the row sums of each of those, and that row sum is a test statistic for one of our samples. We see if it falls into the rejection region. We count how many times, divide it by how many loops, which is 500,000, and the alpha value is 0.05, and it should be. That's a boundary point. Now let's do it for 12, which is another boundary point, and we should get approximately 0.05 in this simulation, and we do. Now in the middle, the power at 11 we said was a little bit over 15%. Let's see what it is, and it is 15.4, or and that's it. So that's it. Let's change these a little bit. Let's change this to a sample size of 55, which then means we have to recalculate the C1 and C2 values. Let's do that, and it goes through all of those. You can tell my machine's pretty slow. There's only one that met the condition. C1 is 588, C2 is 619. They both meet the side conditions met. And let's look at the power curve for this setting. And this is it. Notice that it's still a 0.05 test, right? But the rejection region went from what, 15%, 0.15 to 0.45, right? We increase the sample size, power goes up. We could do a computer simulation on that. This will take a little bit longer because now instead of 25 columns, we have 55 columns. And my machine is incredibly slow, so yours should be much faster. Yep, 46%. That's consistent with what we think. Well, this is all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.